Assalamu alaikum. In this video I'll be showing you how you can create your own line following robot. I will show you what steps I took from all the critical thinking processes to the software implementation and to the final hardware implementation. First of all, what a line following robot is. A line following robot is a robot which follows a particular direction or a particular path, or we can say a track. In our case, our robot is following a 1-inch black colored track, and we are restricted to use our DLD, digital logic design concepts, and build a robot without using any microcontroller or anything like that. Use just simple ICs and other combinational circuit components to create such a robot. So first of all, the basic structure and model of a robot is a three-wheel car, in which we will be controlling the two back tires of the car by using two different motors. Now the first step was to create a logic on which a robot will be making decisions. So for this application we had a black colored track. So for this, the most suitable sensor that we came up with was to use an infrared sensor, because we know that infrared sensors emit infrared rays which are absorbed by black colored objects or any black color material, and it is reflected back by any reflective material or any other color. So it made IR sensor a very ideal choice for application. And in this project we were restricted to use at least 4 sensors, so we used four we are using 4 infrared sensors to make a robot. So now, as we had decided that what our inputs would be, which were the 4 infrared sensors, now we had to know what our outputs will be. So these were to be simply two motors, as our model of our car was a 3-wheel based car, in which we had a freely rotating front wheel and two motor controlled back wheels to the right and to the left. So as we know, how a car simply works. The turning process of a car is that when one of the left or the right wheel is stationary and the other wheel is rotating, so the car takes the turn in the opposite direction, which means toward if the right wheel is stationary and the left wheel is moving, so our car will take a right turn, and when our left wheel is stationary and our right wheel is rotating, so our car will take a left turn. This was simply how a robot would move and take its turns. So now, to make the robot behave according to the inputs that he receives from the sensors of the infrared, we created a logical combinational circuit for this decision making of the robot. So the first thing that we did was to create a truth table. So here I will show you the truth table and explain you how the truth table is functioning. So here is the truth table that we created, in which we have our input sensors here and the output, which are the motors. So we are using 4 sensors, so we decided to decided to assign one sensor to the left, at the left position, one sensor at the right position, one sensor at the center, and one sensor at the back of the car. So the purpose of the left and right sensors was to detect that if there is any turn coming up ahead, that the path is if the path is turning to the right or to the left, and then the center was to keep if to detect if the path is centered, so that the robot can move in a straight path, and the back sensor was to make the robot not get off the track anytime. So for this you can see the outputs, motor right and motor left here. So we created a truth table in which logic was simply based on that if the robot senses the signal at the right sensor, so right sensor, so it will make a right turn. And for the right turn, we know that we need to keep the right wheel stationary and make the left wheel rotate. So similarly, if the robot senses the track path at the left, then the motor right will be on, which will make it turn left. And then we combine it with the center and back, that if the possibilities were that the robot is sensing lines black path at the center and at the right at the same moment, then again it will take a left, again it will take a right turn. And similarly, if it happens that this robot is sensing the left and the center path, then the robot will move towards left. And when the robot was sensing the center path only, then both the wheels will rotate and both the outputs of the motor left and the motor right would be one, and the robot will move in a straight path. The back sensor had to be on the path, for every movement, or else the robot will not move forward. Like if the center path was detected but the back sensor was not on the line, then the robot would not move. Similarly, if it would have sensed left turn and the back sensor was not on the line, again it will not make a left turn, it will just stop right there. So keeping the back sensor on the track was basically, our aim was to make the robot not wobble on the track and go in a straight path and smooth path. So for that we created this whole truth table here. And for that, and to derive the combinational circuitry of that, we used K-maps to derive the equations for our outputs, which were the left and right motors. And we were able to come up with the equations and the expressions, functions for the left and right motors. So now, after deriving the expressions for our outputs, we've first implemented them on Proteus software to check that if our logic was to construct basically the circuit for our hardware, and to verify that is it working according to our specifications or not. So here I have opened the Proteus software where we created the software implementation of this of these expressions and a combinational circuit here. So as you can see, we have 4 infrared sensors here, one labeled back here, one labeled right, one for the center and one for the left. So we to get these sensors in your Proteus, we had to download the library for the infrared sensors, which we did. And then here we have a L298 motor driver, which basically runs our output motors, which we needed to run these output motors. So here we can see our 2 output motors, motor right and motor left. So here are the so for the infrared sensors, we have our VCC pin and a ground pin and an output which we will be receiving from the sensor, and this is the input pin for the Proteus working here, the software working. But in hardware, we know that the input signal will be the black line, which will be with the black track, which will be in front of this sensor, that will be giving us our input our output, change in output, and it will be the input of our sensor. So similarly, I have implemented here using some simple gates and OR gates to create the combinational logic for or to implement the expression that we derived for this robot. And all of the outputs, these are the basically 2 outputs of this combinational circuit. This one right here for the motor left, and this here for the motor right. So both of these outputs are basically going into the motor L298 motor driver, which has basically 3 pins here. We can see here a 12 volt constant voltage, a 5 volt, and a ground. So 5 volt is basically to operate this motor driver, and the 12 volt is basically the higher the amount of voltage we provide here, the faster it will make the motor run or wheel to rotate. So depending on the voltage that we give here, our speed of the robot is being controlled. And we know that a robot, if it is too fast, it might miss out the turns, and not be able to follow the track properly. So we need to keep the speed of a robot or wheel rotations a bit slow, so that it can get enough time to detect the track if there is any curve or any turn coming, and it can quickly adjust its motor outputs according to it. Then we have these outputs 1, 2, 3 and 4, which are basically connected to the motor, to the motor's input and the output. So then we have here these pins here, in which we have the in 1, in 2, in 3 and in 4. So in 4 and in 2 are to be ground, and the wires inputs in 1 and in 3 are basically our outputs from the combinational circuit that we are getting, and these basically determine that which which output wire of a combinational circuit is applicable to which of the motors. So as you can see, in 1 we have given the output of the motor left, and similarly we have connected the motor left at the output 1 and 2, and similarly at the output 4 and 3 we have connected the motor right, and we have given the combinational output of the motor right to the here input 3 of the L298 motor driver. So this is basically how our software implementation is being done here. Now this whole circuit here, we ran our circuit on Proteus, and verified all the outputs according to a truth table, and after varying that, we move towards the hardware implementation of this whole circuit. So first of all, we made a list of all the components that we will be needing. So first we need a line for our chassis kit, and then the infrared sensor modules, so we needed 4 of them, and then we needed one L298 motor driver, then some cell holders to provide constant battery or power source. Then we have IC740, which is basically the AND IC for the AND gates used in a combinational circuits. Then we have the IC7404 for the NOT gates, 7432 for the AND gates. Then this 7812 is to give a constant 12 volt voltage, which we will be needing, as I showed you in our L298 motor driver. We'll be needing it to we will needing a 12 volt supply given to our motor driver, and 17806, which will give a constant 6 volt supply to basically our motor driver and our sensors also. Then we have LEDs and some capacitors and some resistors here, and some jumper wires to make the connection. So first our first implementation was on the breadboard, and where we created this whole combinational circuit that we made on this software. We created that on breadboard on hardware, and then just placed it, or we can say put it on our robot. And here I'm going to show you a video in which you can see that here is our breadboard here, on which all of this circuitry is there that we created on Proteus, and we have placed it here. And these are the IR sensors that we can see here and two. So now let me play this video and show you the whole all for 4 sensors. We can see one is here, one is here, one is here, these 3 sensors, and here we can see these motors here, the right and left motors here, the L298 motor driver, and here is our 4th sensor. So everything is now patched onto this chassis kit, and we can see all the circuitry here. After creating this, patching this on this breadboard, we verified that if our logic was working correctly or not, by making constructing a track, and placing this, attaching all the sensors in their respective positions on the respective positions of the chassis kit, and then running it on a black track. And then uh, after doing this, we were sure that our robot was following the line perfectly, and our logic was working perfectly fine. After all the testing on the breadboard and checking that the robot was perfectly fine, now we had to create, find a more better and optimized and a permanent solution for our circuit to be implemented and to be patched on. So as you know, the breadboard is a very delicate circuitry, so it was quite often when the wires were disconnected very easily, so we needed some permanent solution for that. So that's why we implemented this circuit on a uh, PCB board, and create for that implementation we needed to create a PCB design. So for that, again, we used a Proteus software, and first of all altered the schematic diagram which we made using the sensors and everything. We made a new schematic for the PCB design. So the logic and all the components used, basic components, the gates and the drivers and the ICs, were the components that we were same. So the changes that were needed to be made in this circuit was basically to add the connectors where the battery or we can say the power was to be given, and then place the connectors at all those places where the outputs were to be taken, like the connections for our 4 infrared sensors, and then a motor motor left and motor right outputs, and things like these. So for that we had to use connectors, and then we used silk connectors, place some extra silk connectors, so that if we made any error in making a PCB, so we can use some external wires, jumper wires, and use these silk connectors to to modify our circuit or change anything in the circuit. So then instead we had our constant voltage sources of 12 volt and 5 volt here and 6 volt, so sorry 5 volt. So instead of that, we placed these 7812 and 7806 ICs here, and then all the other circuitry. Then we used the capacitors. We placed the capacitors which were to be needed for the uh, optimal functioning of these regulator ICs. And then all these gates remain the same as they were in the previous schematic. Then we move towards the PCB layout of it. We place all our components here, and route them and connect them to their respective connections. And some of these connections were not able to we tried to keep the maximum of the connections on the single surface, which was the bottom surface. So but some 3 to 4 connections we were not being able to place them on the bottom side, so we had to place them on the top, which were to be connected by using jumper wires. So yes, this is how we constructed a PCB design. So now after a PCB design was complete, we printed it on a butter paper, or you can say sticker paper here. We used a sticker paper and printed it on that, as you can see here. Then we got a PCB board, and here you can see it. We placed our sticker paper, the circuit, on the PCB board, the copper board, and ironed it for about half an hour, and pressed it and due to which a circuit was printed onto that board. And then all the tracks which were a bit disconnected, or not printed on it correctly, we fulfilled these gaps with using a permanent black marker. And this is somehow how our PCB board was looking after the printing of the and completing the tracks of the uh, PCB design. After that, we uh, we dipped it in a FeCl3 chemical, and due to which the copper the copper which was not under the ink all disintegrated, and we were left with this. You can see here design circuit, which the copper circuit part here. And then the next step was to drill the holes where they were to be drilled. So here you can see we were drilled all the holes for the connections and to place our components here. So here you can see this the copper tracks and all the holes that we are making here. After that, we placed all our components in their desired in their specified places. And here we can see then we soldered it accordingly them on their respective places. So then finally our circuit was, as you can see here. Let me zoom in or play this video maybe. And here you can see that after all the soldering and everything, all the components were attached here in this video, you can see. And our design was completed. Our hardware circuit was created here completely. Now the last step was to simply patch this PCB circuit that we created onto the kit, the chassis kit of the robot. And here you can see now this chassis kit has been, from the breadboard, it has been replaced to the PCB, with the PCB here. And one of the obstructions that we faced here was the issue of the battery, as the cells that we first used were simple battery cells, and then we switched on to some LiPo cells, but that was also not useful. Then in the end we used these LiPo batteries that you can see here so with very high mAh power, with around like 1500 to 1700 mAh. So this was sufficient enough to drive our robot for like 30 to 40 minutes straight continuously, and after that we need to recharge it. So yeah, battery was an issue which was dealt with by using these LiPo batteries here with a high mAh power. And after all the patching up, this is how our robot looked. This is another view. You can see here, these are the LiPo batteries that were used. Let me show. So this is basically me showing how this is working, how it is working correctly or not. You can see as I place my finger near at the let me run it again at the right sensor, which means that the right sensor is now getting 0, which means it is reflecting back, and it is working in off condition, and the others are in the on condition, which means that the other side sensor is sensing the black track. So as you can see, the opposite tire is moving or rotating, we can say. So this is how you can see our circuit was working perfect. This is some of the testing videos of our circuit. So now for the final part that we ran so in this video you can see how our robot was working when we finally put it onto a track on the arena, when we ran it on the arena. So you can see how it is following the path smoothly and working correctly. So this is how we created a line following robot. So these are all the steps that I took to create a line following robot, and I hope that after watching this video you would also be able to create your own line following robot very easily, and you have understand all the process and all the procedure that you have to go through to design your own line following robot.